Good afternoon, everyone. So I'm going to speak on the Mahanadi shear zone, whatever work I have done in this shear zone. Actually, I have started this work long back when I started mapping the area as a project of Geological Survey of India. And then after mapping for 1 year, we have done some research project in the same area for another couple of years. And then there also we did some mapping. So these publication which has come recently is actually a combination of all those data and some of my interpretation that we have made through this PhD program. So what today I'm going to speak on the transpressive Mahanadi shear zone, and we have also worked on the symmetry of the shear to prove it a triclinic transpression, and we'll also try to understand its implication in the Eastern Ghats mobile belt. So first, let's have a look at the position of the Mahanadi shear zone in the overall map of Eastern Ghats mobile belt. So this left side map, this one is actually showing the lithozonation map of Mahanadi of Eastern Ghats mobile belt, which was proposed by Ramakrishnan and al. In 1998. And the right one shows the domain and province classification map of Eastern Ghats mobile belt, which is proposed by Dobmeier and Wright in 2003. So according to, and now in both the maps, the Mahanadi shear zone is highlighted in this bold red. Now, if we see in this lithozonation map, the Mahanadi shear zone actually falls well within a single terrain, which is named as Central Migmatite Zone. But if we look at the domain and terrain, domain and province classification map, then we can see that Mahanadi shear zone actually divides two domains: the southern pool. And not only Mahanadi shear zone, there are some other shear zones also marked in this map, which are actually the shear zones have been marked by Chetty and co-workers, and then these has been superposed on the province and domain map proposed by Dobmeier and Wright. So if we superpose these two maps, then we can see that most of the shear zones, it follow the boundaries of the domains proposed by Dobmeier and Wright. So with this background information, we'll go forward and we will have a look at the map, which we have prepared through the work that I have mentioned at the beginning. So me and my field partner, Mr. Tapan Maharana, both of us, we mapped this area in 1:25,000 scale. We did mapping in the southern part of the Mahanadi river. And then while we were doing some research project, we have taken these longitudinal sections, and then we have mapped across this Mahanadi river some areas. So it is not that the entirely area we have mapped fully, this northern part. So we have taken some data, the litho data especially, from the compiled map, which is available online in the GSI portal site, that is Bhukosh. So this is a combined map, the regional map, where I have shown the major lithotypes, which is the pellitic granulites, the chondrites, the charnockite enderbite soup rocks, the quartzofelspathic gneisses, which varies in composition actually, where it is sometimes it is more alkali feldspar, sometimes it is more of plagioclase feldspar, and then sometimes biotites are there, sometimes biotite and amphibole both are there. So variety of the charnockite and quartzofelspathic gneisses are also common in these areas. And now in this map, what we did during our mapping, actually Mahanadi shear zone was a long studied shear zone. The GSI workers started working in this area since 1963. So these are the names mentioned here, who have actually mapped this area in 1:50,000 scale. So they marked in the early 1963 only that there is a high strain zone, and it is defined by the myelonitic foliation, extensive myelonite development along a particular west-northwest direction in the south of the Mahanadi river. So this was a long mapped shear zone. But later on, Nash et al., when he worked on the satellite imagery, he actually identified this lineament as a major lineament and named it as Mahanadi shear zone. Later on, Mahapatra et al. Also worked. They worked from GSI. They did mapping in this area, and they also, like in the eastern part of what is the map shown here, they worked in this area, and they have also come out with a publication where they have mentioned that how the pseudotachylite formation and the mylonite generation are basically belong to two different generations. And then Chetty and co-workers also worked thoroughly in this area through satellite image studies, and they have also mapped Mahanadi shear zone. No, they have also marked Mahanadi shear zone, and they have mentioned presence of transpression along Mahanadi shear zone. Then Mr. Shubham Bose, who was the speaker in the last seminar, actually has extensively worked in this area and have come out with a good number of publications where they have shown that along Mahanadi shear zone, basically in this area, there are two shear deformational events. The earlier deformational events is an extensional one taking place in amphibolite facies grade, and the later one is a simple shear with dextral asymmetry, and which has taken place at a much lower temperature in green schist facies. So these are the major work, the background work, which is available in Mahanadi shear zone. And with this, we mapped this area, and we have demarcated the southern boundary of the Mahanadi shear zone very prominently. But during our mapping, what we have seen is the things, whatever is exposed in the north of the Mahanadi shear zone, like the structural grain, it's all myelonitic. The gneissic foliation is restricted in the south of the Mahanadi shear zone only. And in the south of the Mahanadi shear zone, there are two generations of gneissic foliation. But the thing is, both the things are subparallel at present. The S1 and S2 fabric, which is related to both these deformations, are only separable in the fold hinges, where we can check that there is a high angle between the two. Other than that, everywhere it behaves as a single gneissic foliation. So this is the trend surface map of the area. What we can see is how we could demarcate this southern boundary, that the gneissic foliation in the south of the Mahanadi shear zone takes a dextral bend and becomes subparallel to the west-northwest trend of the Mahanadi shear zone. Now, after crossing the southern margin, everything is west-northwest, and these fabric are basically myelonitic fabric. Now we will have a detailed look in the myelonitic fabric and the gneissic fabric. So south of the Mahanadi shear zone, the things are gneissic fabric. So this was the fold I was mentioning about, the D2 folds, the F2 folds actually. So these are isoclinal folds. That's why away from the hinges, we cannot make out the difference which one is S1 and which one is S2. So it's a composite S1, S2 fabric. But in the hinges, we can make some difference. And from this area, if we look into the thin sections, this is a condylite exposure. So in that case, we can see within the garnet porphyroblast, this earlier S1, it is present at a high angle with the SE, the external foliation, which is manifestation of S2. Now, away from that, everything is the same. There is only one fabric which is defined by, strongly defined by the biotites and the sillimanites. Now, if we look into the Mahanadi shear zone, means south, just north of the southern boundary of the Mahanadi shear zone, then we will see in the field these kind of high strain zones. Means suddenly the planes, the foliation planes will become very close spaced, and there will be visible asymmetry on the plan view. So these kind of features are available in the field, from which we thought it's a myelonitic fabric. And when we look into the thin section, we can see that even the garnet sillimanite bands in the condylite, they show some visible asymmetry in the garnets. So and also by the strain fringes. So these things are available, and in the biotite, we can see some interesting feature. The sillimanite trail inside the biotite, it continues with the outside foliation, and it takes a sigmoidal turn. So all these things together prove that whatever we see in the north of the southern boundary of the Mahanadi shear zone is actually a myelonitic fabric. The earlier gneissic fabric of Pulboni domain south of the Mahanadi shear zone is completely overprinted by this myelonitic fabric. Now, if we have a look at the kind of the shear fabric, then we will see that, especially the mineral assemblage of the shear zone, we will see that the interesting growth pattern of the garnet. This one I have borrowed this figure from Harpatra et al. 2009 because it shows the sigmoidal garnet growth. Now a garnet usually which has already formed will rotate to the in response to shearing, but here we can see the garnet has grown sigmoidally in an asymmetric fashion. So this generally happens when the garnet grows during the shearing. So the shearing was quite a high temperature one, which actually was favorable for formation of the garnet in the chondrites. And then in these two rocks, these actually except this one, all the figures represent chondrites. So in these two we can see that there is brittle ductile deformation in the garnet. So the long tail formation and also this brittle failure. So these also happens, this brittle ductile transition in garnets usually happens at temperature close to 700 degrees centigrade. Now we can see this feature where we can see long quartz with sillimanite inside that. So how a quartz engulf a sillimanite? It happens when 2 or 3 quartz grain fuse together at a high temperature and encloses a sillimanite inside. So this is also a high temperature phenomenon. Now we have plagioclase, which is recrystallized. Now recrystallization of plagioclase also takes place at more than 600 degrees centigrade. Now this one is another photograph from the quartz-feldspathic gneiss within the Mahanadi shear zone. It shows that even if the foliation, the myelonetic foliation is well developed, but the individual quartz grains are pretty strain-free. So this also happens at quite a high temperature where the ribboning is overprinted by the recrystallization and individual quartz grains become strain-free, even if the elongation is still visible. So next we will come to the sense of the shear. So geometry of the shear zone. So what we did to understand whether there is a strike slip component of the shear, we studied the horizontal sections. And to check whether there is a dip slip component of the shear, we studied the vertical section which have strike perpendicular to the strike of the shear plane. So these two sections we have targeted for our preliminary study. Now we can see the horizontal sections represent a very good dextral sense. By the CC dash fabric in the field, by this quarter fold in the photomicrograph surrounding a garnet, by this delta porphyroclast K-feldspar where the strain fringes form the dextral sense of movement. And in this one, in this vertical sections, Mahanadi shear zone is northeast dipping. So we can see the northern side is upthrown from these fold, from these lens, quartzo-feldspathic lens, asymmetry of this quartzo-feldspathic lens, and from these asymmetry of the detached band of quartzo-feldspathic bands. So these things represent that the northern side, means the hanging wall side, is actually upthrown in case of Mahanadi shear zone. So for the simple shear, the dextral horizontal and slightly an upthrown component, these together form that the simple shear component is actually oblique. Now, when we have an oblique simple shear component, now next we will try to see whether there is any pure shear component or not. Now, when we see some of the porphyroclasts in the Mahanadi shear zone, we find a very interesting feature. Now, this is a section of the megacrystic charnockite from the Mahanadi shear zone. Now, this is the overall shear direction, this arrow. Okay. Now, if we see at the porphyroclast, in most of the cases, the strain fringes indicates yes, it's a it's parallel to the rotation of the porphyroclast is in agreement with the movement direction, shear direction. But in some cases, there is some exception, like this case, like this case, like this case, where the long axis of the porphyroclast is actually dips opposite to the dips towards the movement direction and indicates an opposite sense. So these kind of things are actually back rotated clast. So when we get the back rotated clast, if we have a look at the work of Simpson and Dipau 1993 and their subsequent works, we can see that if there is a pure shear component along with the simple shear component, at that time only we can expect back rotated clast, because the simple shear component will always try to rotate all the grains in the same direction, means towards the direction of shear. Now, if there is a significant pure shear component in this direction, then some of the clast which are making small angle with the shear plane, they will move towards they will rotate towards the opposite direction due to this pure shear component. So that happens here. So there is a simple shear component and there is a pure shear component. So when these two components are there, and especially in this direction, there is a pure shear component. So it is matching with a shortening direction. So this kind of thing actually indicates that there is chance of transpression. So before going to transpression, because I have many friends which are not from this like a hardcore geology field, so I will just explain in brief what is transpression. Transpression is a scenario where simultaneously there is a strike slip movement, and along with that, which is non-coaxial, and along with that there is a shortening component which is pure shear and coaxial. So this can be represented by this block, which is the explanation of Sanderson and Martin in 1984. In this one we can see that this one there is a strike slip component. For that
properly.
Oh, is it?
Yeah, if you can just share your stop your sharing your video, it might help, because the bandwidth is really low.
I will do that.
One of the suggestions is that you can switch off your video. That might help.
Yeah, sir, I'm trying that. Yes, sir, I will do that. Sir, I'll just stop. No, I'll just stop the video, right, sir?
Don't stop sharing. Just
yeah.
Just switch off the video.
Just switch off your camera. That's all.
Just right icon of the there are 6 icons, right, in the bottom. The second from the
sir, I got it. Sir, I got it.
Okay.
Sir. Sorry, sir.
Fine. It's okay. It's okay.
Yeah. Is it fine now,
again,
sir?
No. Again, you. Yeah. Fine. Thank you.
It is fine now, sir.
Go ahead.
Yeah.
Earlier
okay.
it was okay.
So yeah. So
yes.
What happens in case of a transpression, due to this strike slip movement, suppose this block, which was a parallelopipe initially, this is the shear zone block, will become a rhombohedric block because of the strike slip component. And because there is a pure shear component in terms of shortening, these two wall blocks, unsheared blocks, will try to move towards each other, and this will create a vertical stretch in this direction. This was Sanderson and Martini's model, because if these two press together, there will be an extra volume which will try to move somewhere. So Sanderson and Martini said it moves vertically, straight upward. But later on, Forsen and Tikoff has worked out different direction of movement for this extra mass, for this extra volume. So these are the different directions where the stretching is possible. So with this background, what we did, we tried to have a look at the scenario of Mahanadi shear zone. So we have established that there is a southern block, unsheared block, which is full bony domain. Northern block we have not studied in this study, but yes, it is there. And then the wide Mahanadi shear zone in between. So this northern block is actually upthrown, as I have shown there, and it's an oblique slip movement, which has been confirmed from the shear zone perpendicular section and the horizontal section. So this is an oblique movement. Just take the pointer. So this is an oblique movement for the simple shear, oblique direction. And because we have some back rotated clast, and not only in one section, if we see this section, there is back rotated clast, and if we see this section, there also we noted back rotated clast. So we can for sure say that there is a pure shear component which is actually causing stretching of this block. Now in this case, the strain will not remain a plane strain anymore. So it's a non-plane strain, and since we have strike slip and shortening together, it's a transpression. So this is the schematic transpressive model of the Mahanadi shear zone. Now, when we have confirmed that it's not a simple shear alone, it's a subsimple shear from the pure shear component, we tried to determine the kinematic vorticity number. And for that, we have chosen two planes. One is perpendicular to the strike of the shear zone, a vertical plane, this one, this blue plane, and another one is this brown plane, which is at an angle to the shear plane, but its strike is parallel with the shear plane. Now, in both the cases, we have come out with a kinematic vorticity number. We have used Porphyro class hyperbolic distribution method for calculating the kinematic vorticity number, and we have come out with the number of 0.44 and 0.48. Now, in two planes, we are having WK value, which is between 0 and 1. Which is a very important, which has a very important significance. If we look into the work of Forte and Bailey 2007, what they said that if a shear zone is having monoclinic symmetry, it will show, if it is a subsimple shear zone in a transpressive case, it will show only 0 and 1, something between 0 and 1 WK value only on the vorticity profile plane. But in all the other plane, it will show WK value equal to 0. But in our case, we are not seeing this. We are seeing that we have at least two planes where WK values is between 0 and 1. So this is the case. Where in the second case, they have shown that not only on the vorticity profile plane, in the other planes also, in case of a triclinic shear, symmetry shear, the WK value will be between 0 and 1. So this is our case. Now, apart from that, we also noted one interesting feature, which is variation in plunge of the stretching lineation. Now, in the field also, or in the stereographic projection also, this has been depicted, that the myelonetic foliation, the average myelonetic foliation is this, and it almost maintains a constant orientation. But when we look at the lineation, it actually varies over the foliation. So this happens when the symmetry of the shear zone is triclinic. All these workers have worked in these scenarios and have come out with the conclusion that if there is a variation in stretching lineation on the shear plane, in that case, we can conclude that the shear zone is a triclinic symmetry. For better understanding this situation, we have taken help of some block diagrams. Now, I'll explain what is this diagram is. So these I have made this following the work of these authors, which I've mentioned at the bottom. So there are three components. This is a progressive deformational case. So there are three components. One is a block diagram that shows the actual movement, and there is a strain ellipsoid that shows the maximum, intermediate, and minimum stretching directions. And there's a stereographic projection which shows the position of the maximum stretching direction and its projection on the shear plane. Usually when I measure the stretching lineation in the field, we measure it on the shear plane. So what we measure its projection in most of the time. So we are interested to see how the projection varies on the shear plane. So for that, these diagrams have been prepared. Now, in case of simple shear, we can see that this x direction, which is the stretching lineation, maximum stretch direction, will change, but its projection will always remain in the same place. It will change in space, like it is moving, but its projection will always remain in the same place. And finally, if we try to fit a two-fold rotation axis in each of the case like this, we will be able to do that. Okay, so these simple shear is having a monoclinic symmetry. If we look into this shear zone block, now we will have a look at the subsimple shear, where the stretching is in the horizontal direction, means in the same direction of the simple shear. Okay, there is a component of pure shear also, but the stretching of the excess volume is restricted to this shear direction only. So in this case also, what happened, the stretching lineation, the maximum stretching direction will vary in space, but its projection will be on the same spot on the shear plane. Now we will move on to the next case, which is the case of Sanderson and Marchini, where the pure shear component causes vertical stretching of the shear zone block. Now in this case, okay, I just forgot this. Here also, if we try to fit a two-fold rotation axis, we'll be able to fit that, because this plane and the other side plane are absolutely same in all the angles. These angles are 90 degrees. So it will fit, the two-fold rotation axis will fit. Now when we look at the Sanderson and Marchini case, we can see that this vertical stretching, due to this vertical stretching, the maximum stretch axis, after moving in this horizontal plane, it will move on to vertical position. That's what Sanderson Marchini has said. So either we'll have stretching lineation in a horizontal horizontal direction on the shear plane, or it will be vertical, So this is the Sanderson and Marchini case. But here also, if we fit a two-fold rotational axis in the shear zone block, it will still give a monoclinic symmetry, because these angles still remains 90 degrees. So if we rotate in a two-fold way, it will repeat itself. So we will get a two-fold rotational symmetry, monoclinic one. Now we will come to the triclinic case. What happens in the triclinic case? Like the Mahanadi shear zone. Now this pure shear component is there, and this simple shear component is causing an oblique motion. Now due to that obliquity, the shear zone block will be of a shape where this angle will no more remain a 90 degree. So this angle between the three axes, alpha, beta, gamma, will be non-equal angles. What happens in case of a triclinic symmetry? So that's why this is called triclinic symmetry. And if we have a look at the stretching direction, it will move in space. Not only move in space, it will also move on the shear zone boundary, means shear plane. Its projection will also move on the shear plane. So that's why in case of a triclinic symmetry, we have variation in stretching lineation. Now, if we compare all the things together, we can see in case of simple shear, in case of subsimple shear, these projection will be having a fixed position. It will not at all move, the stretching lineation. But in case of transpression, in case of monoclinic symmetry, it will be either horizontal or vertical. But in case of triclinic, it will actually move. Now, if we superpose our case in Mahanadi shear zone, here the shear zone is, I have considered this for vertical for like ease of drawing, but here in my case it is inclined. So now on the shear plane, we can see the variation of stretching lineation. So this can be explained by these experiments, the block diagrams. So now I will come to the regional perspective of the same. So if we say that Mahanadi shear zone, we have established it as a wide shear zone located in the northern segment of Eastern Ghats mobile belt, well within the Phulboni domain. We have established that Tikarpara domain doesn't exist because it's all myelonitic foliation. There is no gneissic fabric in that domain, and also the lithology continues from Phulboni domain to Tikarpara domain. So there is no reason for defining it as a separate domain. So it's a well single domain thing, and the Mahanadi shear zone is a wide shear zone within the northern segment of the Eastern Ghats mobile belt. Now this Eastern Ghats mobile belt and Singhbhum Craton, these were collided in a situation where there was a transpressional regime. It was first told by Bhattacharya et al., Bhattacharya 1997. Later on, Mukhopadhyay and Boshak in 2009, they have also explained that the indentation of Eastern Ghats mobile belt into the Singhbhum Craton was an oblique one, and that has caused the bend of this northern portion of the Eastern Ghats mobile belt. Now, when we have an oblique indentation, oblique stress, direction of stress, in that case only we can expect strike slip, and depending on the obliquity, we can also express some pure shear. So this is the case what has happened here. And Mahanadi shear zone, though it is not a boundary shear zone, it is actually a far field response of the amalgamation of the two terrains. So it's a far field response of the same. And Chetty at 2014 also supported this transpressive regime in Mahanadi shear zone. So we can think and explain Mahanadi shear zone as an intra-terrain transpressional zone formed due to the far field stress of the amalgamation of Eastern Ghats mobile belt and the Singhbhum craton. Now, when we establish this as an intra-terrain one, we can just have a relook at the shear zone and dominal classification of Eastern Ghats mobile belt, and we can see that there are many shear zones which have actually demarcating the boundaries of these domains. So I think we should have a relook on the boundaries, how far those are intra-terrain boundaries, and is there any chance of being intra-terrain boundaries. So in that case, the case of Mahanadi shear zone actually lead us to think in that way also, whether the dominal classification is absolutely justified or based on proper ideas, or only it is based on the shear zones. So that, I think, that has to be relooked. So I think that's it I wanted to say from my side. And thanks to all of you for being a patient listener. And especially I would like to acknowledge Geological Survey of India for giving all the logistic support for carrying out the field work and all. And I am grateful to my supervisors who have actually guided me to carry out these work. And also my friends for always being a support, my teachers who are here and who actually created the foundation on which I'm today standing, and also my colleagues who have always supportive to me. And lastly, Dr. Abhinav Roy, because he's a constant encouragement and inspiration to me all the time. So thank you so much.